We're practically swimming in data these days. It's everywhere. But most of it is just chaos, a massive, unlabeled jumble. So what if we could teach machines to look at that mess and find the hidden patterns, the secret structures, all on their own? Well, that's the incredible promise of unsupervised learning. Let me ask you this. Imagine I handed you an entire library, but none of the books had titles, there were no genres, not even a card catalog. Where would you even start? How would you organize it? That's the exact challenge we're throwing at machines. And believe me, the way they're solving it is changing everything.
So to really get what makes unsupervised learning so special, it really helps to see it next to its more famous cousin, supervised learning.
Okay, think of it like this. Supervised learning is like studying for a test when you have the complete answer key. You show a machine a million pictures, each one carefully labeled cat or not a cat, and eventually it learns to predict the answer. But unsupervised learning? That's like being an archaeologist digging in the dirt. You're just finding artifacts. There's no answer key. Your job is to just find the patterns, to piece together the story from the clues you find. Yeah, we're not telling the machine what to look for at all. We're basically setting it loose on this raw data and just saying, go discover something interesting. It has to find the surprising groups, the hidden connections, all by itself. All right, so how does a machine even begin to discover anything? Well, one of the most powerful and fundamental ways is by finding natural groups in the data. We call this process clustering. Just take a look at these dots on the screen. Without me saying anything, your brain is already trying to group them, right? You're seeing the distinct clusters. And that's the exact same intuitive task we give to a clustering algorithm, but we ask it to do it on a scale that our eyes could never, ever handle. The whole idea is actually pretty simple. Things inside a group should be as similar as possible, and the groups themselves should be as different from each other as possible. And this gets used everywhere. I mean, from segmenting customers for marketing campaigns to identifying different types of ecosystems in environmental science. But here's the thing. Real-world data is messy. It's just not going to fit into neat little circles. So instead of forcing things into these hard-edged boxes, a much smarter way to think of clusters as these overlapping zones of probability. It's kind of like mixing together a bunch of different bell curves to get a much better picture of the data's true shape. And the results? They can be absolutely amazing. Get this. If you treat every single pixel in an image as its own little data point, defined by its color, a clustering algorithm can group all the similar ones together. And just like that, it automatically separates the lizard from the rock. No human had to tell it what a lizard was. Okay, so let's shift gears a bit. We've talked about finding groups of things, but what about finding the rules that connect them? This next technique is called association rule mining, and it's all about discovering those hidden relationships. This is the classic example you always hear about, the market basket problem. So a store analyzes all its sales, and it finds this rule. Now, what does this mean? Support tells us that computers and antivirus software are bought together in 2% of all transactions. But confidence? That tells a much more interesting story. It means that out of all the people who bought a computer, a whopping 60% of them also bought antivirus software. Now that's an insight you can really use. This is the invisible engine that powers so much of modern retail. It's what decides which products end up next to each other on the shelf, which items get bundled together for a special offer, and what that website recommends to you right before you check out. It's finding all those, if you like this, you'll probably like that patterns that we all create. And the way it works is actually pretty logical. First, the algorithm just combs through all the data to find any combination of items that show up together frequently. Once it has that big list of popular combos, it then starts generating rules from them. But only the strong rules, the ones that have a really high level of confidence. For our final technique today, we're going to tackle one of the biggest headaches in data science, just having way too much information. This is the art of dimensionality reduction, or, to put it simply, finding the signal in the noise. Think about trying to describe a car. You could list hundreds of different features: horsepower, torque, wheelbase, headroom. It's overwhelming. Dimensionality reduction finds a way to boil all that down into just a few key ideas, maybe like performance or luxury, without losing what makes each car unique. It's all about finding a simpler but often more powerful way to tell the story. Look at this. It's a perfect example. On the left, if we just plot two of the raw measurements from these flowers, the different species are all mixed up. It's a jumbled mess. But on the right, An algorithm has found a totally new angle to view the exact same data. And from this new perspective, these principal components, the groups just pop. They become crystal clear. It didn't change the data, it just found a better way to look at it. And the power of this is just, it's hard to overstate. This is incredible. Researchers took genetic data from thousands of Europeans and fed it to an algorithm. Critically, there was absolutely no location info, none. The algorithm reduced the insane complexity of all that DNA down to its two most important components of variation. And then it just plotted each person on a chart, and the results? A near-perfect map of Europe. It emerged purely from the hidden patterns in the data. Mind-blowing. So we've looked at three really different approaches, right? Three ways that machines can learn and find patterns without any teacher, without any answer key. And each one is an incredible tool for discovery. So, to recap, we've got clustering, which is all about finding those hidden groups. We have association, for uncovering the secret rules and relationships. And we have dimensionality reduction, which helps us simplify all that complexity so we can finally see the big picture. And this is so much more than just a cool academic idea. Unsupervised learning is a real engine of innovation. It's how medical researchers are discovering new subtypes of diseases. It's how astronomers classify galaxies that are billions of light years away. It's how we can even begin to make sense of a world that is generating more unlabeled data every single second. And that really leaves us with one final and kind of exciting thought. As our ability to just collect data continues to explode, the real frontier isn't analyzing what we already know how to label. It's about discovering the patterns we never even knew existed. The biggest secrets are still out there, hidden in the chaos, just waiting for the right algorithm to come along and find them.